Hello, this is Math 2115 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled More Proof Tradecraft. And I encourage you, as always, to be an active learner when watching this video. When we left off, you were to prove by cases the statement known as the triangle inequality. Perhaps you finished this, but if not, you have time now. You know what to do. Let's see how you did. So the two cases we're going to look at are x plus y is bigger than or equal to 0 and x plus y is less than 0. So let's look at the first case. If x plus y is bigger than or equal to 0, we have the absolute value of x plus y is just x plus y. And x is less than the absolute value of x and y is less than the absolute value of y. So the triangle inequality is true in this case. If x plus y is less than 0, then the absolute value of x plus y is equal to the negative of the quantity x plus y. You see, if x plus y was 5, or was minus 5 rather, the absolute value of minus 5 would be 5, and that's a minus 5. So then we distribute that, but now the absolute value of minus x is certainly less than or equal to the absolute value of minus x, and minus y is less than or equal to the absolute value of minus y. But the absolute value of minus x is the absolute value of x, and the absolute value of minus y is less than or equal to the absolute value of y, or actually it's equal to. These both are equal to. So you see we've proven it in each of the two cases, and we're finished with this proof. Here's another problem for you to do. I'm asking you to prove that m cubed plus 2n squared is equal to 36 has no solutions in the positive integers. You know what to do. Let's see how you did. This is a case where we can do complete enumeration of all the possibilities, and it's an exhaustive proof. So let's consider if m and n are positive integers, and if m is bigger than 3, that means 4 or more, then m cubed plus 2n squared is bigger than 36. The reason that is true is, for example, if this is 3, that would be 27, and this one were totally 0. It's bigger than 0, but if it were 0, then that would not be true. But if this is 4, we would have 4 cubed, which is 64, and so this would certainly be bigger than 36. So you see, if m is bigger than 3, then that's certainly true. And so what we're going to do is, we know that m then, the only thing we have to consider is m being 1, 2, or 3. Similarly, if n is bigger than 4, meaning starting with 5, this would be 50 here, so this certainly would be true. This is a positive number, so m cubed is going to be positive. So the only thing we have to consider is n being 1, 2, 3, and 4. So we look at the calculation of m cubed plus 2n squared for all of these possibilities. There are only 12 of them, and we see that none of them are 36. So we've proven that there are no solutions in positive integers for this equation for m and n. Here's another one. We are to prove that this equal this has no solutions in positive integers. You know what to do. Let's see how you did. Well, this one you can't do that because there are an infinite number of positive integers. I suppose you could try to move this over, but it's much more complicated. The easy and correct way to probably approach this problem is, notice that this one, that's an even number, and that's an even number, so that means this is an odd number, and here this is an even number. So those two things can't be equal because One is odd and one is even. Some theorems are the form P if and only if Q, and you remember that that means you're really going both ways. So P if and only if Q means if P then Q and if Q then P. So you have to prove this. To prove this, you have to prove both directions. Now some theorems are true from an if and only if standpoint. For example, the Pythagorean theorem. If c squared equals a squared plus b squared, then the triangle is a right triangle. And if it's a right triangle, c squared equals a squared plus b squared. So that goes both ways. But both directions must be proven separately. Now, the converse is not always true, even if the conditional statement is true. For example, if x is 2 and y is 3, then x times y is 6. That is true. But if x times y equals 6, it does not follow that x equal 2 and y equal 3. We could have x to be 1 and y to be 6 as an example. We also will talk about existence proofs. A proof there exists an x that satisfies some predicate statement is called an existence proof. And one way to prove this is to exhibit a member, A, in the domain of discourse that makes P of A true. Now, such a proof is called a constructive proof because you actually showed an example. And we've talked about constructive proofs. But sometimes it is possible to give a proof that does not exhibit an element that makes P of A true. And usually these are proved by contradictions or something similar to that. But these are called non-constructive proofs. Now, although constructive and non-constructive proofs are equally valid and satisfying mathematically, non-constructive proofs may give no clue how to find the item proven to exist. Some engineers are less enamored with such an approach. Different tastes, perhaps. We have already done a non-constructive existence proof. This card problem that we did earlier in the course is an example. Later in this lecture, we will speak of a constructive existence proof. There's another example for you to do. Prove A is a subset of B if and only if the complement of B is a subset of the complement of A. You know what to do. Let's see how you did. Well, these statements actually are contrapositives of each other, so that's all you really need to say. This says if x is an element of A, then x is an element of B. This says if x is not an element of B, then x is not an element of A. So those are contrapositive of each other and hence are logically equivalent. Here's another example for you. Disprove the statement for every positive integer n squared is less than or equal to 2n. You know what to do. Let's see how you did. Well, 3 works because if you take 3 squared you get 9 and 2 cubed is 8. So you've given a counterexample. A note of encouragement by way of analogy. It took most of us the better part of a year to learn to walk. When we got older, most of us learned to ride a bicycle. Some of us, but way fewer, learned to ride a unicycle. Please note, proofs are not easy. They are a higher level and different kind of skill. If you work hard enough at them, they will come. Don't stop believing in yourself. I will not. Another analogy. According to the U.S. Golfing Association, a golfer is allowed to have 14 clubs in his bag. This may include a bunch of woods, a bunch of irons, and some other clubs. We have discussed several proof techniques, and there will be more coming. Why do we need so many? It's similar to golf. Depending on the shot you need to hit, a different club may be appropriate. Depending on what you're trying to prove, one approach, a proof technique, may be superior. Like golf as well, different clubs may be used with success depending on the skill of the golfer. Different proof techniques may be used depending on the skill and the courage of the student. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.